Hi, everyone. Welcome back after the break. So in this half of lecture, we're going to talk about roots in prime modulus arithmetic. So we've done division, we've done powers. Now we're going to try the reverse powers, which are roots. But of course, reversing is hard. Now, addition, multiplication, and exponentiation are relatively easy because you're just going forward in each step. But reversing things, subtraction, division, and roots are reversing those operations, and sometimes they're much harder. So for example, when we were doing this for ordinary arithmetic, in order to reverse addition and get subtraction, we had to invent new numbers. We had to invent negative numbers. For division, we had to invent fractions. For roots, we had to invent irrational numbers. In modular arithmetic, it's also hard, but for a slightly different reason, which is that these methods are just a lot more complicated. So like multiplication was easy in modular arithmetic because all you had to do was you multiplied and then you took the remainder after dividing by the modulus. But for division, you had to look at a times table and try to figure out what number matched, or you had to use the Euclidean algorithm, or you have to use Fermat's little theorem, as we just gave you a moment ago. So now, reversing is hard, but it is something that we still care about doing. And so we're going to be talking about how to reverse roots. But let's remind ourselves how we did division. So there are a couple ways we did division. The easiest way, or not easiest necessarily, but if you have a full multiplication table, then which includes all pairs of products, you could just look for the reverse. So to remind you all, for example, if you had 2 divided by 7 mod, 2 divided by 5 mod 7, well, what you need is you need x such that x times 5 is congruent to 2 mod 7, right? What times 5? So you're looking in the 5 column here. What times 5 is equal to 2? Well, 6, right? So 6 times 5 is congruent to 2 mod 7, and therefore 2 divided by 5 is congruent to 6 mod 7. Okay, so that was division, and you can just reverse it by looking it up in the table. One way of looking up roots is also to do that. So this is slightly different, but if you have a powers table, so here's the powers table for mod 7 up to x to the 13. Well, a square root of a number a is a number b such that b squared is congruent to a, right? And there might be multiple numbers. So for example, the square root of 2. Well, in order to find the square root of 2, you need to find a number b such that when you square it, you get 2. Well, this happens for 2 different numbers. So the square root of 2 is either 3 or 4. These are both square roots of 2. And you can double check this because you'll notice that 3 squared is congruent to 9, which is congruent to 2 mod 7. And 4 squared is congruent to 16, which is also congruent to 2 mod 7. Okay, so if I give you a powers table, you can pretty easily figure out the roots by just looking to see, what things squared give you the number 2. And you can generalize this to kth roots. So a kth root of a is a number b such that b to the k is congruent to a. So that's easy enough. So for example, a 5th root of 2, which you could also write as 2 to the 1/5. Sorry, let me not write it there. Which you could also write as 2 to the 1/5. But what does that equal to? Well, you look in the column for x to the 5 here. Let me do this in a different color. So look in the column for x to the 5 there. Well, when is that equal to 2? Well, when that's equal to 4, so it's just 4. And you can double check this because 4 to the 1 is just congruent to 4. 4 squared is congruent to 16, which is congruent to 2. And then 4 to the 4 is congruent to 4. So then 4 to the 5 is congruent to 4 to the 4 times 4 to the 1, which is congruent to 4 times wait, did I do that right? 4 to the 5, 4 to the 4, 4 times 4, which is congruent to 16, which is congruent to 2 mod 7. Okay, yep. Okay, does that all make sense? So all you're doing is you're doing the reverse. And so if I gave you the table, you could just look up the reverse. So let's have you all try that out. So, excuse me. I give you the powers table. And I'm not going to ask you the answer. I'm just going to ask you how many answers each of these has. You should find the answer, of course. But it was just easier to ask you how many answers each of these has, because sometimes there will be multiple answers and sometimes just one. So what's the cube root of 5 in mod 7 arithmetic? How many answers are there? Okay, it looks like people are guessing A for 0. And that is indeed correct, because if you look up here in the cube root column, so in the cubes column, you can't ever get 5. You only ever get 1 and 6. And so no roots exist. Okay, let's try the next one. What about the cube root of 6? Yeah, so you just look in the cube column and you're like, oh, well, I have 3 different examples of 6 appearing there. So this is actually either 3, 5, or 6. So 3 roots. Okay, what about the 5th root of 2? Okay, so the 5th roots, you're looking in this column here, and you're looking to find when 2 appears. 2 appears here, and so this is just congruent to 4, and there's only 1 root. So this is a unique answer. Okay, what's another one? What's the 5th root of 3? Let me keep on using green. Okay, yeah, so the answer is again 1, because the 5th root is 3. That's this here. So 5 to the 5 is equal to 3, and so this is congruent to 5. So that's, again, 1 root. Okay, what about the 13th root of 2? Okay, so the 13th root of 2, that's here and here. And so that's just congruent to 2. And you only get 1 root again. Okay, so we've done a couple examples now. So now you should be thinking like a mathematician. When do kth roots exist in mod P arithmetic? When are kth roots unique? When is there only 1 root? And so if you look at the mod 7 table, how do you figure these things out? Well, this is the same sort of question as we did earlier with our times tables, right? Like when do you, or with these powers, you're just looking for when do you get all, how can you solve without the table? That's a very good question. We're going to get to that. It's quite hard. So that will be the subject of this lecture. But here we have a table, so it's a little bit easier. But when are the kth roots unique? Well, in mod 7, they're unique when you see an example of all of them. So clearly, the first roots are unique, right? So if you take the first root, by which I mean don't do anything to it, well, clearly those are all unique. Well, it's also true when you take the 5th root. You get each number appears only once, and every number does appear. Also for 7, also for 11, and also for 13. And you note that these repeat, right? Because of course you know that the powers repeat. And so in mod 7, kth roots always exist and are unique for k is equal to 1, 5, 7, 11, 13, and so on. Okay, and notice that whenever they're not unique, that means that some other root doesn't exist, right? Because if they're not unique, then that means that some root was, some number was duplicated, appeared twice, and that meant that some number didn't appear. Okay. So now, if we had a lot more time and this were a class where, what I would do is I would make you guys break up into small groups, and then you would sit down and you'd solve a bunch of these tables. But that would actually take a really long amount of time because these powers tables take quite a bit of time to compute. And then what you do is you look to see what was unique with that whole thing that we did like last week. But now, wrong way. So you can write out all these different tables for small primes, look at all the columns with all of these numbers and try to find the pattern. So I'm just going to go ahead and give you the numbers k such that we can always find kth roots. Can you spot the pattern? And because this pattern is a little bit complicated, I'm going to leave this, I'm going to give you a couple of options. So what is the pattern of all of these numbers? So there are a couple of things you might notice. So you might notice some things that are true, even if they're not always true. Or they're not true for every single thing. So I noticed that some people said that they're all prime numbers, but you have to be a little careful. Is 9 a prime number? They are all odd numbers, and this will generally be true. So they will always all be odd numbers. But I mean, it's obviously not all of the odd numbers. So like you're missing, for mod 7, you're missing 3. Okay, so I'm going to go ahead and give you the punchline here, which is that all these numbers happen to be relatively prime. So these are all numbers that are relatively prime to p minus 1. Okay, and don't worry, I'm not really expecting that you would have noticed that pattern. But since it takes a lot more time to figure out that pattern. But if you stare at these long enough and you build enough of these tables, mathematicians at one point realized, oh, wait a moment, all of these numbers happen to be relatively prime to p minus 1. And this sort of makes sense, right? Because p minus 1 seems to be special for powers. We already showed that with Fermat's little theorem, right? So p minus 1 is special. And what we need is for all these numbers to be, if the number is relatively prime to p minus 1, then somehow all the roots exist and they are unique. Yes, also 25 is not prime either. So these are relative primes. Okay. We'll come back to that, don't worry. So let's remind ourselves about a couple of the prime modulus facts. So importantly, you can always uniquely divide by any number except 0 in the prime modulus. So say 2 over 5 mod 7. Well, we know how to do this. So we know 7 is equal to 5 times 1 plus 2. 5 is equal to 2 times 2 plus 1. 2 is equal to 2 times 1. And so 1 is equal to 5 minus 2 times 2. 1 is equal to 5 minus 7 minus 5 times 2. 1 is equal to 5 times 3 minus 7 times 2. And so the 1 is congruent to 5 times 3 mod 7. So 1/5 is congruent to 3 mod 7. And then 2/5 is congruent to 6 mod 7. Okay, you can always uniquely divide by any number except 0 because you can find reciprocals when you're in the prime modulus. And then we also had Fermat's little theorem. And note, this is quite important, that we had this p minus 1 term here. So that p minus 1 term is what we need to be relatively prime to. And so a to the p minus 1 is congruent to 1 mod p if a is not congruent to 0. And of course, this is what we just did in the last part of lecture. So 2 to the 6 is congruent to 1 mod 7. And 2 to the 600 is congruent to 2 to the 6 times to the 100, which is still congruent to 1 mod 7. And so things like 2 to the 602 is congruent to 2 to the 600 plus 2, which is congruent to 2 to the squared, which is congruent to 4 mod 7. Okay, so these are some of the facts about prime modulus that we already know. But now let's think a little bit about how we would take roots in ordinary arithmetic. And then we'll come back and try to figure it out for prime modulus arithmetic. So I'm going to ask you a relatively simple question. Without using a calculator, which of the following numbers is a square root of 1024? It's a little bit harder without a calculator, right? Okay, but people still seem to recognize that it is 32. And you can figure this out by just multiplying 32 by 32, and you do get 1024. But now, on the other hand, suppose I ask you a slightly different question. Suppose I told you that 1024 is equal to 2 to the 10, which it is. Then I ask you which of the following is a square root of 1024. So this ought to be a little bit easier, right? Because if 2 to the 10 is 1024, well then 2 to the 10, the square root of that is just equal to 2 to the 10 to the 1/2. And you multiply this together, so that's just 2 to the 5, which is of course equal to 32. So somehow, if I gave you a prime factorization, then finding the square root would be easy, right? Okay, so now suppose I did the same thing for you in mod 7. So let's say that in mod 7 arithmetic, what is the square root of 2? Now, you guys have no idea how to do this, right? Because like you could write out the entire table and you could figure it out from there. But what if I told you that 2 is congruent to 1024 mod 7? Then which of the following is the square root of 2? Oh, well, let me zero that out before you guys reply. So somehow, if I told you in advance that 2 is congruent to 1024, then it should be a lot easier to figure out what the square root is. So let's try to figure this out. Well, what we then know is we always know that 2 to the 5 times 2 to the 5 is congruent to 2 to the 10. But of course, that implies that the square root of 2 to the 10 is just 2 to the 5. So the square root of 2 is congruent to the square root of 2 to the 10, which is congruent to 2 to the 5, which is congruent to 32, which is congruent to 4 mod 7. Okay? So somehow this is a lot easier whenever you're working with, whenever I give you the powers already. But you have to be a little bit careful about this because sometimes the answer is not unique. So what if I told you, for example, that 2 is congruent to 9, which is congruent to 3 squared? Then which of the following is the square root of 2? Try not to overthink this. Okay, yeah, so it's just 3 because the square root of 2 is congruent to the square root of 9, which is congruent to 3 mod 7. Okay, so the answer is both of these numbers are actually square roots of 2 and mod 7, because as we said, they're not always unique. Because notice that our power, we're in mod 7 arithmetic, and the number 2 is not relatively prime to, or sorry, it is not relatively prime to 6. So you don't get unique answers here. But if I were to give you, the sort of power breakdown, if I gave you this number written as a power of a number, then finding the square root is a lot easier because then you just divide that power by 2. And this method you can turn into a more general method for finding all of the roots, which is you try to write your number as some power of a number, and then you just divide. So let's see. So in higher roots, so for example, in mod 7 arithmetic, what is the fifth root of 2? Well, here's a strategy that might work by making use of Fermat's little theorem. We want to find an equivalent of 2 as a power whose exponent is a multiple of 5, right? Because if you can find something that's something to a power of something that's a multiple of 5, then you can just divide by 5, and then that gives you the final answer. So let's try this out. Well, the fifth root of 2, oh, sorry, not the square root of 5, the fifth root of 2. Well, remember Fermat's little theorem, which is 2 to the 6 is congruent to 1, right? So if 2 to the 6 is congruent to 1, then that implies that 2 is congruent to 2 times 1, which is congruent to 2 times 2 to the 6, which is congruent to 2 to the 7, right? So earlier, we were using this method to take big powers and make them smaller. But of course, you can also use this method to make little powers and make them bigger. Now, why would you want to do this? Well, because as you make these powers bigger, maybe you'll find one that's divisible by 5. So we have 2 is congruent to 2 to the 7, which is congruent to 2 to the 13, which is congruent to 2 to the 19, which is congruent to 2 to the 25. Right, so all of these things are, this is all true by Fermat's little theorem in mod 7 arithmetic. But you'll notice that here we have a power that's divisible by 5. So that means that the square, so instead of 5 minus 1, it's 5 plus 1. So each time here we're adding 6. I'm not entirely sure what you mean by plus or minus 1. But so each time here we're adding 6 instead of subtracting 6. But yeah, so if we were just trying to find the fifth root of 2, well, that's equivalent to saying, well, we're trying to find 2 to the 1 over 5, which is equivalent to saying this is 2 to the 25 to the 1/5, which is equivalent to saying this is 2 to the 5, which is equivalent to 32, which is equivalent to 4 mod 7. Okay, and the reason this works is because using Fermat's little theorem, you can make the powers bigger, or you can make the powers smaller in a particular way by just adding 6 to it each time or subtracting 6 from it each time. Like that's why division by remainder work, or division with remainder work. Here, we're just trying to find something so that it exactly divides into whatever root we're looking for. And then that gives you some answer that is the answer. So now, if you were doing this on an exam, what I would suggest you do is then you take 4 to the 5 and then ask if that's equal to 2. Exercise to check. 4 to the 5 is equivalent to 2 mod 7. So I'll leave that in your own time, but you should be figuring out ways of checking your work. So nearly everything that's going to be in this class, there are ways of checking. And if you check all your work, and then that'll at least tell you on the exam if you got the right or wrong answer. Yes, x to the p minus 1 is equivalent to 1 mod p. That is Fermat's little theorem. Yep. It's a very important theorem for this class. And in general, like not just for this class, in number theory in general. Okay, let's have you all try it out. So in mod 7 arithmetic, what is a fifth root of 3? So of course, you'll be using the same strategy that we did for the last one. Okay, we're starting to get some answers. Well, what are we going to start out with? Well, we start out with 3 to the 6 is congruent to 1. So we know that 3 to the 1 is congruent to 3 to the 7, it's congruent to 3 to the 13, it's congruent to 3 to the 19, it's congruent to 3 to the 25. We notice that this, taking the 5th root of 3 and taking the 5th root of 2, the process is basically the same. So plus we have that 3 is congruent to 3 to the 25, which implies that the 5th root of 3 is congruent to 3 to the 25 times 1 over 5, which is congruent to 3 to the 5, which is congruent to 3 to the 4 times 3. Well, let's figure that out. 3 to the 1 is congruent to 3. 3 squared is congruent to 9, which is congruent to 2. And then 3 to the 4th is congruent to 4. So this is congruent to 4 times 3, which is congruent to 12, which is congruent to 5. Okay, so that's fairly straightforward, right? But of course, it's still a little bit painful to have to keep on testing. So you keep on trying different powers and seeing if it's divisible, right? So it'd be nice if you had a general rule for figuring out when one of the powers is divisible and which one it is. It turns out, if we think about it, we can figure that out. So let's think about this backwards, and then we'll think about it forwards. So to solve the kth root of A mod P, we need to find a number B such that B to the K is congruent to A mod P, right? Well, that's just the basic problem setup. So for example, the cube root of 2 mod 11, well, the answer, if we knew the right answer. So if you wrote out all the powers tables, you could just get this by staring at it. 7 cubed is congruent to 343, which is congruent to 2 mod 11. Okay, so if I wrote out the entire powers tables, you could just look at it to find a number B such that B to the K is congruent to A. But another way of seeing it is to see if there exists some power M such that B is congruent to A to the M. This will not always work, but it will always work under a certain condition. In particular, it will always work, which we'll discuss in a moment. So for example, if you had powers of 2, 2, 4, 8, 16, which is just 5, 10, which is just, well, 10 is still 10 in mod 11. Then 20, which is just 9, and then 18, which is just 7. Oh, hey, this does exist such numbers. So 2 to the 7 is congruent to 7 in this in mod 11. So if we had tried to use powers of 2, we would have gotten this answer eventually. When does this work? This works precisely when there exists some A to the mk that's congruent to A mod P, right? Because what you're doing is you're looking for a multiple of K. You're looking, looking for a multiple of K such that A to the mk is congruent to A. And in this particular case, so we have 2 to the 7 times 3 is, well, that's obviously 2 to the 21, which is congruent to 2 mod 11, because we know that 2 to the 10 is congruent to 1, right? By Fermat's little theorem. And so if you had done this the way we did on the previous slide, you would have gone, well, 2 is congruent to 2 to the 11, is congruent to 2 to the 21. Oh, hey, 21 is divisible by 3. And then you know the answer was 2 to the 7. Okay, so that's working backwards. But now, of course, the general problem is how do you go forward to figure this out? Oh, wait, what just happened? No, that was the wrong button. Go away. Okay. I think that was the recording button or something. Anyway, keep on going. So when does that strategy work? Well, what we need is A to the km is congruent to A mod P. Or in other words, we need an exponent that is a multiple of K such that the two numbers are equivalent. Well, what do we have? We have Fermat's little theorem, which says that 1 is congruent to A to the P minus 1. But that means it's also congruent to A to the P minus 1 times any L, right? So if 1 is congruent to A to the 6, then 1 is also congruent to A to the 12. It's also congruent to A to the 18, and so on. So all the multiples of P minus 1 are congruent, those powers are all congruent to 1. So that means that A is always congruent to A to the any multiple of p minus 1 plus 1, right? Just by multiplying on both sides by a. So that's the general format of things that are equivalent to a. So another way of saying this is we need to find mk, or km, equal to L times p minus 1 plus 1. Because, of course, the right-hand side here are all the equivalent powers, and the left-hand side are the multiples of k. And now I'm going to rewrite it. We can rewrite this as 1 is equal to mk minus L times p minus 1. What does this look like now? Well, remember, we are given k and p minus 1. And so what we're doing now is we're just trying to find a combination of k and p minus 1 that's equal to 1. And of course, we know how to do that. That's one of the first things we learned back in week 1 of lecture. Or was that week 2? It might have been week 2. But where we were finding combinations of two numbers. And you can always find a combination for 1 if the greatest common divisor of the two numbers is equal to 1. Or in other words, if the two numbers k and p minus 1 are relatively prime. And so this method, this particular method always works if the two numbers are relatively prime, which means that you get a unique root for every single number. This particular method will not work in the case where you have multiple roots or no roots. But it will work in the case where you have a unique, exactly one root. And so this method will sometimes work for roots, but not always. And so let's rewrite this forward again. So this is an algorithm for b congruent to k, the kth root of a mod p. Important. This algorithm works if p is prime, a is not congruent to 0 mod p, and k is relatively prime to p minus 1. So note that this is required for Fermat's little theorem. And this is needed to find a linear combo for 1. Okay, so there may exist roots when these conditions aren't satisfied, but this particular method won't work without it. So what is the method that we're going to describe now? So the first thing you do is you find 1 equal to mk times 1 as a combination of k and p minus 1 using the reverse Euclidean algorithm. So for example, what is the cube root of 3 mod 11? Well, the first thing you need to do is you need to find the greatest common divisor of 3 and 10, which is going to be equal to 1. So that's k, and that's p minus 1. Well, 10 is equal to 3 times 3 plus 1. So 1 is equal to 10 minus 3 times 3. And if you have to be a little bit careful with signs here. So I'm going to rewrite this as 1 is equal to minus 3 times 3 minus 1 times 10. And you note that, of course, this here is k, and this here is L. And so this here is M, and this here is, oh, sorry, that wasn't L, that was p minus 1. And this here is L, okay? So you're going to rewrite it in this format. Once you've done that, then you know that the kth root of a is just congruent to a to the m mod p. And you have to be a little bit careful about this because what we have here is you have 3 to the minus 3. So, let me rewrite this a little bit more clearly. 3 to the minus 3. So b, the root, is congruent to 3 to the minus 3. And there are a number of ways you can do this. One is you could solve the reciprocal and then multiply it a couple times. The other way of doing this is you notice that this is congruent to 3 to the minus 3 plus 10, right? Because by Fermat's little theorem, 3 to the 10 is equal to 1. So this is congruent to 3 to the 7 mod 11. You can break this up. This is congruent to 3 times 3 squared times 3 to the 4th. Well, 3 is congruent to 3. 3 squared is congruent to 9. 3 to the 4th is congruent to 81, which is congruent to 4. This is all mod 11, of course. And so therefore, this is congruent to 3 times 9 times 4 mod 11. And when you multiply that out, that's congruent to 9 mod 11. Okay, so that's a lot. And of course, you want to check at the very end that b to the k is actually congruent to a mod p. And you can do this by just taking 9 cubed and checking to see that this is 9 cubed is equal to 3 mod 11. So ideally, you want to check this, and that should be relatively straightforward to check. Okay, this is a lot, so I'm going to work another example in its entirety before making you guys do it. So let's work an example. Let's find the fifth root of 10 mod 13. Let me use a different color. Let me use black actually. I don't use black often enough. So the first step is find one as combo of 5 and 12. Well, and why 12? Because 12 is 13 minus 1. So 12 is equal to 5 times 2 plus 2. 5 is equal to 2 times 2 plus 1. And then 2 is equal to 2 times 1. So 1 is equal to 5 minus 2 times 2. 1 is equal to 5 minus 2 times 12 minus 5 times 2. So 1 is equal to 5 times 5 minus 12 times 2. Okay, and of course this here is k, and this here is p minus 1. So this here is m, and this here is 2. So note that the powers are positive this time. M is positive this time, which makes life a little bit easier. And so then what we know is therefore, we know that the fifth root of 10 is congruent to 10 to the 5, because of m, mod 13. Another way of seeing this is if you had done this the other way, you would notice that 10 to the 25, because of course that's 5 times 5. 10 to the 25 is congruent to 10 to the 12. It's congruent to 10 to the 12 times 2 plus 1, which is congruent to 10 to the 1 mod 13. Okay, so if you had just like listed out all things that are equivalent, you would have gotten to 10 to the 25. Okay, but having said that, well, let's solve this. So 10 to the 1 is congruent to 10. 10 squared is congruent to 100, which is congruent to 9. So you have to be careful. This is mod 13 now. 10 to the 4th is then congruent to 81, which is congruent to 3. And so then 10 to the 5th is congruent to 10 to the 4 times 10, which is congruent to 3 times 10, which is congruent to 30, which is congruent to 4 mod 13. That's your final answer. But of course, it's important to check your work. So how do we check this? We check to see if 4 to the 5th is congruent to 10 mod 13. So is it? Well, 4 to the 1 is congruent to 4. 4 squared is congruent to 16, which is congruent to 3. And 4 to the 4 is congruent to 9. So 4 to the 5 is congruent to 9 times 4 is congruent to 36, which is congruent to 10 mod 13. So that all works out. Any questions about all that? It is a lot of different steps, but it's all things you already know how to do. So we've learned the Euclidean algorithm way back when, and it turns out that you can use it in many different ways, including for this particular problem. So let's have you all try it out. And I'm going to go ahead and give you the steps there. So just repeating the steps in short. You have to make sure that p is prime and the greatest common divisor is equal to 1, and then you can solve it. So what is the cube root of 6 mod 17? Okay, so we're starting to get a couple answers in. So let's just go through all the steps again. So we need to find 1 as a combo of 3 and 16. Well, that's pretty straightforward. 16 is equal to 3 times 5 plus 1. And so therefore, if you rewrite this in that shape, 1 is equal to 3 times minus 5 minus 16 times minus 1. Oh, sorry, if we write this as 1 is equal to 16 minus 3 times 5. We're going to rewrite it in the same format so we can figure out what m and L are. So here, m is minus 5, and L is minus 1. So the solution is just 6 to the minus 5 mod 17. But I don't particularly like 6 to the minus 5. So instead, I'm going to add 16 to it. And so, or this is equivalent to 6 to the 11 mod 17. So that's a positive power. And you just need to compute that. So 6 to the 1 is congruent to 6. 6 squared is congruent to 36, which is congruent to 2. 6 to the 4 is congruent to 4. 6 to the 8 is congruent to 16, which is congruent to minus 1, which makes life a little bit easier. And then so 6 to the 11 is congruent to 6 to the 8 times 6 to the 2 times 6, congruent to minus 1 times 2 times 6, which is congruent to minus 12, which is congruent to 5 mod 17. Okay. I'm getting a couple quizzical looks. If anyone has any questions about this, please ask me right now. The basic idea is you need to find it as a combination. You have to put it in the right format because you need to figure out, the important thing is figuring out what this m here. M is the important quantity. And then after that, then you just multiply it out and then you figure out what the answer is. Okay, and let's finish off in our last couple minutes of class by asking you all to do one more of these. So let's try the 4th root of 6 mod 17. How are things going? Is something going wrong? Yeah, so you have to be really careful, right? Because you need the greatest common divisor of k and p minus 1 to be equal to 1 in order for this method to work. There may exist roots, but the method we just gave you will only work if the two numbers are relatively prime. And so our list method doesn't work since the GCD of 4 and 16 is equal to 4. Okay, so the answer here is none of the above for the purposes of this method. One of these numbers might well be the 4th root of 6. I didn't actually check, and hopefully they're not, but they might be. But the key here, though, is that if you're trying to solve it using this method, it won't work. Okay, and with that, always check your conditions, always check your work at the end of the day. Hopefully, this was not too confusing. But yeah, that is the end of today's lecture. Reminder that your homework is due on Friday. So please do your homework. You guys should have all the pieces you need for that. Hint, use Fermat's little theorem, as we've been doing over and over again. I have not graded all your quizzes yet. I am slowly reading through all of them. Some of them are quite interesting. But yeah, so with that, I will see you all on Monday. Bye, everyone.